So when we think about the last few years, right, the global response to all the health crises, it really saw buildings everywhere just scrambling to upgrade their indoor air quality,
Yeah.
their IAQ.
A massive scramble. Yeah.
Exactly. But the rush to deploy solutions, whether we're talking hospitals or schools or even offices,
Right.
it often resulted in this huge spending on technologies that were, well, fundamentally siloed. They were really designed to address one half of a two-part problem. So for our deep dive today, our mission is to get into the technical literature you've shared. We really need to expose why relying on these common single-function air cleaners is often, well, just an insufficient technical solution.
And then show what's next.
And more importantly, uncover the innovative engineering that is finally bringing a comprehensive approach into a single unified architecture. We're definitely moving beyond the basics today.
And that leads us, directly to the core thesis from all this material: optimal indoor air quality. It really necessitates a true two-pronged attack. Right, you just cannot successfully manage indoor air by focusing only on particle removal or only on proactive sterilization. The systems have to integrate both functions.
Because they're connected.
Fundamentally, they are tackling interconnected problems. So if you ignore one side of that equation, you are introducing some major and, frankly, preventable technical failure risks into your environment.
Okay, so let's start with a foundational view of the current landscape.
Yeah.
Because that's where the limitations really become apparent. For most facility managers or system engineers listening, the market is just dominated by two big, distinct categories.
That's right. So first up, we have what everyone knows as air purifiers.
Right.
And these are defined by mechanical filtration. The ubiquitous HEPA filter high-efficiency particulate air, that's the gold standard.
Right.
And their job is vital. They mechanically capture airborne particles, dust, pollen, pollutants, pet dander, all the physical stuff that causes respiratory irritation.
And the mechanical nature of that capture, that's their strength, but it's also their critical weakness.
Exactly. Their strength is capturing particles, typically down to 0.3 microns with really high efficiency. But their inherent limitation is that, while they're incredible at trapping particulates, they're completely passive when it comes to the biological threat.
So they don't do anything to kill what they catch.
They lack the capacity to actively neutralize or eliminate viable microorganisms. We're talking airborne bacteria, mold spores, viruses. They hold them, but they absolutely do not destroy them.
And that brings us to the second category, the air sterilizers. These systems use technologies like ultraviolet light, so UVC, or maybe advanced plasma ionization methods.
Yeah, their core function is basically the opposite of the purifiers. They aim to inactivate or destroy airborne pathogens in flight.
And I'm guessing their limitation is just as significant.
It is. Because they're designed to use energy fields or light to kill, they fundamentally do not address the physical contaminant load.
So they don't filter.
They don't effectively filter or remove the mass of particulate matter, the PM, the dust, the big aerosols that are just floating around in the air. If your air is full of physical pollution, a sterilizer won't clear it up.
So on paper, a facility manager might think, okay, simple, I'll just use both. I'll filter the particles and then I'll blast the air with UVC.
This seems logical.
But the technical reality, which your source material really lays out, is that the problems are so tightly correlated that even running two separate systems can still leave you exposed to failure.
And this is where we really have to shift from just a discussion of product features to, understanding the urgent technical need for integration. Particle removal handles physical contaminants. Sterilization handles the biological threat.
Yeah.
But you are absolutely right. They are not independent variables.
They're profoundly intertwined.
Profoundly.
So tell us more about that technical correlation. The sources you found cite a relationship between particulate matter concentration and the transmission rate of things like COVID-19. What's the mechanism behind that link?
Well, the scientific findings are pretty striking. There's a documented, highly positive correlation between the general ambient particulate matter concentration.
So like PM.
Exactly, PM. And especially PM 2.5, right? That airborne matter that's 2.5 micrometers or less in diameter. So a correlation between that and the transmission rates of SARS-CoV-2. And this isn't just an epidemiological observation. It gets into some fundamental aerosol physics.
So the PM itself isn't just inert pollution floating around. It's somehow active in the transmission side.
Precisely. The research suggests that PM 2.5 acts as a potential carrier for these
A
bioaerosols.
scarier.
Yes. When an infected person exhales, the virus is in larger droplets that fall pretty quickly, and also in smaller aerosols that can stay airborne for, well, almost indefinitely. But these smallest aerosols, which often carry the viable virus, can actually adhere to or get encapsulated by the existing particulate matter in the air.
And one of the sources called it a booster. Are we just talking about physical transport here, or does the particulate matter actually change the viability or the infectious potential of the virus? Because that sounds like a pretty big distinction.
That is a critical question, and the source material really emphasizes the physical transport mechanism. The PM acts as a delivery vehicle. A single, tiny viral aerosol might settle out of the air quickly on its own.
Right.
But once it attaches to a larger piece of dust or smog, the PM, that larger particle can then be carried much further and for much longer by just general air currents and ventilation patterns.
So the PM is literally boosting the range of the pathogen.
It is. It's transforming what might be a localized risk into a widespread one.
That clarifies the link beautifully. So if you only focus on killing the pathogen, but you leave all these physical carriers floating around for hours,
Right.
or if you only filter the carriers, but you leave the pathogen viable and free-floating, you've completely missed the point.
You've missed the point.
And this brings us squarely to the two primary technical failure modes that result from relying on single-function systems. Let's really dive deep into the first one, the shielding problem.
The first failure mode is a limitation of disinfection or sterilization systems because of the reality of particle-borne pathogens. We just established that pathogens hitch a ride on particulate matter.
Okay.
Now, think about your UVC or your plasma system. These sterilization methods are super effective against a free single pathogen cell, but they often fail completely when that pathogen is shielded.
And what's shielding it? Is it just dust?
It's the physical structure of the fine particulate matter itself. PM, especially indoors, isn't always a perfect little sphere. It often consists of these irregular, aggregated, or porous structures. Think of it like a microscopic, complex mineral sponge.
A sponge.
And the pathogen is nestled deep inside the pores or aggregated right in with the structure.
So the UVC light, which needs line of sight to damage the DNA, it hits the outside of this little dust particle. But the pathogen deep inside is completely safe.
Exactly. The particle acts as a physical bunker. The UVC intensity might decay rapidly as it tries to penetrate the particle structure, or the irregular shape just creates shadows. The pathogen stays viable, protected by its little carrier.
And then you inhale it.
And when that particle is inhaled, the protective structure is often dissolved or stripped away by your respiratory tract, releasing a fully viable pathogen right where it can cause an infection. The sterilization system looked great on its spec sheet, but it failed to reach its target.
That is a fundamental flaw. And the second failure mode is, in many ways, even more counterintuitive and, you could argue, more alarming, because it involves the systems we engineers trust the most, the high-efficiency purifiers. This is the microbial reservoir risk.
This is the really critical downside of relying only on mechanical capture. When microorganisms like bacteria, mold, fungal spores are physically trapped on the dense matrix of a conventional filter,
They aren't destroyed.
they're not destroyed, they're simply immobilized, they've been captured, which is good, but they are still potentially viable.
And under what conditions does this immobilized threat turn into a reservoir?
We're talking about environmental conditions that are common in almost any HVAC system, especially sustained warmth and high humidity. If the filter is dense, say a MERV 16 or a HEPA filter, it captures moisture very efficiently. So when that filter media gets damp and warm, those trapped, viable microorganisms have the perfect incubator. The filter essentially becomes a localized reservoir for microbial survival and growth.
So instead of an air cleaner, we've actually and accidentally designed a potential bioreactor right inside the ventilation duct.
That's a great way to put it.
Did the sources provide any data on how often this kind of secondary contamination actually happens in real-world systems?
While it's hard to track universally, the risk is very widely recognized in HVAC engineering literature, especially when you're talking about fungal and bacterial growth and filters that are poorly maintained or maybe too dense for the conditions. And the consequence is significant. Proliferate.
It multiplies.
The captured organisms multiply and can then be re-aerosolized, released back into the airstream. And that increases the risk of secondary contamination well beyond what you started with. This is why capture must be coupled with immediate, reliable inactivation.
The message is crystal clear. Single-function systems are subject to these inherent technical trade-offs, particle shielding in the sterilizers and the microbial reservoir risk in the purifiers.
Right.
So if conventional methods are failing on both counts, the only path forward has to be true integration. And this brings us to one of the most promising emerging technologies highlighted in the research for overcoming these constraints, MESP, the microelectrostatic precipitator.
MESP is a fascinating solution because it seems to be engineered specifically to bridge these two failure modes. It delivers high-efficiency, simultaneous filtration and air disinfection
At the same time?
within a single cohesive system architecture. And crucially, it does this while fundamentally changing the energy equation for high-performance air cleaning.
Okay, let's get into the specifics, especially for the engineers listening. How does MESP achieve this integration? It's all based on carefully controlled electrostatics, is that right?
It's all about precision charge management. So the process begins upstream with ionization. MESP uses a precisely controlled high-voltage charge grid, we're talking several kilovolts, to ionize the air.
Oh.
The purpose here is not just random static charge, it's to ensure that every single airborne particle, including those really challenging submicron particles and any bioaerosols stuck to them, acquires a robust, defined electrical charge before it even gets to the collection stage.
So you're not just hoping the particle randomly bumps into a fiber, you are actively turning the pollutant into a targeted magnet.
That's it, exactly. And once charged, these particles move to the next stage, collection via electrostatic media. The MESP system uses an energized PP electrostatic media, PP standing for polypropylene,
Okay.
and those charged particles are efficiently just pulled right out of the airstream through an intense, strong Coulombic attraction.
And that strong, directed attraction has to be the key differentiator from a mechanical filter. Why use that PP electrostatic media specifically? And what's the big engineering benefit of swapping Coulombic attraction for just sheer physical blocking?
Well, the material science of PP is critical here. It has excellent dielectric properties, meaning it can sustain that high electrostatic field really effectively. But the real engineering advantage is in the pressure penalty.
Oh, the lack of one.
Or rather, the lack thereof, yes.
Let's elaborate on that pressure
Yeah.
penalty, because that defines how facilities managers have to run the numbers.
Absolutely. To get the same air quality as, say, a MRV16 or a full HEPA filter, you need an incredibly dense mechanical matrix, and that density dramatically restricts the airflow.
Right.
We're talking about a fan needing 30 to maybe 50% more energy just to push the specified CFM, the cubic feet per minute, through that dense filter bank. This means bigger fan motors, higher CapEx, and significantly higher OpEx over the life of the unit.
And MESP avoids this.
It does,
Yeah.
because it achieves its high capture efficiency by attracting the charged particles, not by relying on a dense physical barrier to physically block them. The pressure drop across the MESP filter media is dramatically lower than a comparable HEPA filter.
Which changes the whole energy calculation.
It changes it overnight. Engineers can achieve high-efficiency particle capture, including submicron capture, with a much lower fan static pressure requirement. And that leads directly to major energy savings and often allows for smaller, quieter HVAC systems overall.
That's a huge operational advantage. Now, we've covered the ionization and the low-pressure collection, but we still have to address the microbial reservoir problem. Where does the destruction part, the inactivation, fit into this process?
It's fully integrated. The inactivation function is delivered as part of the collection process itself. Remember, that energized collection surface doesn't just capture the particles.
Okay.
The continuous high-intensity electrostatic environment that's maintained on that collection surface is lethal to the pathogens.
So the pathogen is neutralized the moment it lands. The
Yeah.
possibility of survival or proliferation is gone.
Exactly. The electrostatic environment disrupts the cellular or viral structure right on contact, actively contributing to microbial inactivation. This completely bypasses the microbial reservoir risk because the particles and bioaerosols are neutralized as they're captured, instead of being left to potentially breed in some warm, damp media.
This sounds almost too good, you know. It addresses particle shielding by charging the particle itself. It avoids the reservoir risk with constant inactivation, and it eliminates the energy-sapping pressure penalty. So what are the common counterarguments or trade-offs that MESP engineers still have to manage when they're designing these systems?
That's a fair point. I mean, any advanced technology has trade-offs. For MESP, the primary engineering consideration compared to traditional mechanical filters is managing ozone generation, especially at high voltage.
Ah,
MEST systems have to be designed very carefully to operate within strict regulatory limits, which they do by precisely controlling the charging grid voltage and optimizing the air velocity. Also, while the collection media has a long lifespan, engineers have to account for periodic washing or cleaning of the collection cells to maintain peak efficiency. That's a different maintenance cycle than just swapping out a disposable HEPA filter.
sure.
But for many environments, the energy savings and the integrated sterilization benefits just far outweigh those operational considerations.
Okay, so let's unpack this. We started by looking at why single-function air cleaning is just riddled with these failure points, from physical fielding that protects pathogens to the microbial reservoir risk created by dense mechanical filters.
Mhm.
And we've ended by dissecting an integrated solution, MESP, that seems to address both the physical and the biological problems simultaneously.
And I think the takeaway for anyone involved in building design or facility management is pretty profound. Clean indoor air is not achieved by simply filtering or sterilizing. You have to tackle both challenges at the same time within a coherent, optimized system.
We have to move past those fundamental limitations.
The particle shielding and the microbial survival inherent in these older segregated technologies, yes.
So creating healthier and safer indoor environments requires a commitment to integrated systems. Systems that address both the physical structure of the particulate matter and the viability of the bioaerosols.
And if we connect this to the bigger picture and the engineering trade-offs we spent some time on, that infamous pressure penalty, there is a final thought for you to chew on.
Okay.
Conventional dense mechanical filters, they create massive resistance. They require more energy, they limit practical airflow. If an innovative engineering solution like MESP fundamentally eliminates that pressure penalty with electrostatic collection, how drastically does that change the total system design calculus for large-scale, energy-efficient IAQ system deployment in enormous commercial and residential settings? It really redefines the very economics of air hygiene.
An essential thought for anyone considering their next HVAC retrofit or new build design. And for those of you who are curious to see the technical specifications of MESP and its collection mechanisms, the source material pointed toward the AQT webpage where you can explore the solutions further.